Okay, so today we will see what we mean by monotone sequence. Okay, so monotone sequence. So before that, we'll see what we mean by increasing sequence and decreasing sequence. Okay, so increasing sequence means what? Let x is equal to xn be a sequence of the real number. We say that the sequence xn is increasing if it satisfies the inequality. x1 is less than x2, less than x3, and dot dot dot. That means what here? The values of the first term, then second term is increased. So that means what? We have the term increasing in order. Okay. So that means what? The second term is more than the first term. Third term is more than the second term. Fourth term is more than the third term, and so on. Okay, so that is the increasing sequence. So we'll define a decreasing sequence. Okay, so let x is equal to xn be a sequence of real number, Okay, so we say that sequence xn is decreasing if it satisfies the inequalities. So that means what? Your first term is more than the second term. Okay, the values are going to decreasing now here. What? x3 dot dot dot. This is what? xn plus 1 dot dot dot. So this is what? Decreasing sequence. Now we'll see monotone sequence means what? So monotone sequence. Okay. Let x is equal to xn be a sequence of real numbers. Okay. The sequence xn is said to be monotone. Sequence if it is either increasing or decreasing. That means what? If a sequence is increasing, then it is called monotone sequence. If a sequence is decreasing, it is also called a monotone sequence. So monotone means what? It is either increasing or decreasing, not both of that. Okay. So if it is increasing sequence, then it is called monotone sequence. Okay. So now we'll see the monotone convergence theorem. Okay. Monotone convergence theorem. Monotone convergence theorem. Okay, so statement. A monotone sequence is monotone sequence of real numbers is convergent if and only if it is bounded. Moreover, if x is equal to xn is bounded increasing sequence, then limit n tends to infinity, xn is equal to supremum of xn, n belongs to n. supremum n belongs to n. Okay. Second, if x is equal to xn is bounded decreasing sequence, then limit n tends to infinity, xn is equal to infimum of xn n belong to n. Xn. That means what is this? Monotone convergence theorem. Every monotone sequence means what? Every increasing or decreasing sequence of real number is convergent, then if and only if it is bounded. Okay. So if we have the monotone increasing sequence, show that it is a bounded sequence. Okay. So if you want to discuss the convergence or divergence of the monotone sequence, just show that it is bounded. Okay. So if you prove it is bounded, then what? The sequence will be convergent. Okay. So if you want to discuss the convergence of the monotone sequence, just show that it is bounded. Okay. So that means what? If a sequence is increasing, now see the first term is the lower bound. First term will be the lower bound of the sequence. Only we have to show that it is bounded above. Only bounded above. That means what? This theorem tells you that if a sequence is monotonic increasing, show it is bounded above. Right? So monotonic increasing sequence bounded above is bounded because x1 will be the lower bound of this one. Okay. So if a bounded means what? It has a lower bound and it has the upper bound. Okay. So that means if a sequence is monotonic increasing sequence, just show it is bounded. That means show it the upper bound is exist, right? And then that sequence is always convergent to its supremum. Supremum is what? The smallest of all upper bound. The smallest of all upper bound. Okay. So and infimum is what? It is called the greatest lower bound. Okay. So greatest of all lower bound. Okay. So now if a sequence is decreasing, now see this is the upper bound. It is the first term will be the upper bound. For decreasing sequence, you have to show that it is bounded below only, right? So if it is bounded below, right? So if a monotone sequence with decreasing sequence is bounded below, if you prove it is bounded below, automatically it will be the bounded because what? The first term is your upper bound. So whatever you have to show that it is only the bounded below. So that means if a sequence is bounded below, now here decreasing sequence, just show it is bounded below, and then it will be what? It is bounded sequence. Okay, and it will be bound by monotone convergence theorem. So it is what? Convergence sequence, and it converges to its infimum. Increasing sequence, it converges to supremum, and decreasing sequence is converges to infimum. Infimum is here now here. Okay, so that we have to prove now this. We have to prove this one. So this is the if and only part. So for that, what we have to do? So first we have to assume that a monotone sequence of real numbers is convergent. We have to prove this is bounded. Okay, and the second part which will take it is bounded sequence. It is monotone and it is bounded. Okay, so then we have to prove it is a convergent. Okay, so we'll take a part one. Proof. Part 1. Assume that a monotone sequence of real numbers is convergent. Okay, so we know that if a sequence if a sequence is convergent, we have proved this is convergent, then it is bounded. Okay, so therefore a monotone sequence of real numbers is convergent, then it is bounded. Then it is bounded. Okay. So first part is over because we have already proved that every convergent sequence is bounded. We have already proved that every convergent sequence is, whatever this is monotonic sequence, but we have given that it is a convergent. So that means if it is increasing and convergent sequence, then it is bounded. If it is decreasing and convergent, so it is bounded because what? It is convergent, right? Every convergent sequence is bounded. Okay. So the first part is very easy. So first part is over now here. So now we take a second part. Second part, you have to take a monotone sequence. Okay. So part second. Assume that a monotone sequence of real numbers is bounded. Okay. What is our aim? Our aim is to prove that x is equal to xn. Assume that a monotone sequence, we will say here monotone sequence x is equal to xn of real numbers. We'll write here. Assume that a monotone sequence x is equal to xn of real numbers is bounded. Okay. So we have to prove that x is equal to xn is convergent. Okay. So case 1, x is equal to xn is increasing sequence. Okay. So what is our aim? To prove that limit n tends to infinity, xn is equal to supremum of xn n belong to n. Okay. This is our aim. So that means what? We are trying to prove the sequence is increasing now. Okay. It is monotone, means it is increasing or decreasing. So in case 1 we have taken this as increasing. In case 2 we will take this as decreasing. So what is our aim? To prove that limit n tends to infinity, xn is equal to. That means we have to prove that the sequence xn is convergent. Okay. So that we have to prove. Okay. So x is equal to xn. Okay. Let yes, we will say s. Xn n belongs to n. So this is non-empty set is not. What we are given that it is bounded. We are given that is non-empty set and it is bounded. So therefore it has supremum. It has supremum. Okay. It has supremum. It has also infimum. It has supremum and infimum. Okay. So in case 1 we will take only the supremum, and in case 2 for decreasing we will take the infimum now. It has supremum. Say u. So u is the supremum of this one. So u is equal to supremum of s. U is the supremum of s. Okay. So for given epsilon greater than 0. So u is the supremum. U is the that means what? U is the supremum means what? No number less than u is an upper bound of s. So give a for given. So u minus epsilon will not be an upper bound of s. Will not be the upper bound of s. So it is not upper bound. That means what? There exists xk belong to s such that, because it is not upper bound means what? So upper bound is here, that means all the numbers are less than that number. So u minus epsilon is not upper bound. So that means what? So this there, that means what? U minus epsilon be somewhere. Now there exists xk such that will not be upper bound. So that means what? U minus epsilon is less than xk such that U minus epsilon is less than xk. Okay. So but x is equal to xn is increasing. It is increasing sequence. So therefore U minus epsilon is less than xk is less than xn for all n greater than k. For all n greater than k. Right? So but U is the supremum. U is the supremum. Okay. So this implies that U minus epsilon is less than xk is less than epsilon is less than U is less than U. Why? Since U is equal to supremum of S. That means all the elements of S are less than U. So this is xn. So this is true for all n greater than or equal to k. This is true for all n. Okay, so we write here this as for all n greater than or equal to k, since U is equal to supremum of S. Why we have written S, U here? Because U is the supremum. All the numbers of S are less than U. So we will write this as U minus epsilon is less than xk is less than xn is less than U is less than U plus epsilon is less than. I can write this what? Because epsilon is positive. Okay. So U is less than U plus epsilon. So what we have here? So this implies that U minus epsilon is less than xn. This is true for all n greater than or equal to k. Okay. So this is what? U plus epsilon. Now what does this imply then? This implies that mod of xn minus, this is true for all n greater than or equal to k. This is very important now. Here my minus U is less than epsilon for all n greater than or equal to k. So this implies that limit n tends to infinity xn is equal to U, and this is nothing but the supremum of xn, n belongs to n. Okay. So now the first part is over. Okay. So I have proved that if a sequence is bounded, then it converges to its supremum. Okay. So now in the second case, so we'll take a second case now. Case second. Case second. X is equal to xn is monotone is decreasing. Is monotonic decreasing means it is decreasing and bounded. What we have to prove? It is convergent and converges to its infimum. Okay. So let S is equal to xn, n belongs to n, is bounded. Let S is equal to x. Okay. So S is non-empty and bounded, non-empty and bounded set. Okay. So therefore S has infimum. F has infimum. Say I will take that infimum is also U now. No problem for this one. Okay. So for given epsilon greater than 0. Okay. So now U is the infimum. That means what? It is the greatest lower bound. That means what? No, this is the greatest one. This is the greatest one. Right? So no number greater than U. No number greater than U is a lower bound of S. No number greater than U is a lower bound. So what? For given epsilon greater than 0, U plus epsilon will not be a lower bound of S. Lower bound means what? See here. Okay. Now this is your U, right? And all here the lower bounds are all are the real bound. Okay, because all the numbers of S are greater than these numbers, and this is what the greatest lower bound, greatest of all lower bound, greatest of all lower bound. Okay, so now this is not a lower bound. U plus epsilon is somewhere now. Okay, that means what, this is your U plus epsilon. That means what, in between U and U plus epsilon there is a, in between U and U plus epsilon there is a number in S. In number S there exists at least one number in S such that it is lies between this U and U plus epsilon. So therefore there exists xk belongs to n, xk belongs to x such that U plus epsilon xk, xk. Okay, but x is equal to xn is decreasing sequence, so therefore xn is less than xk is less than U plus epsilon for all n greater than k, Okay, so but U is the infimum, but U is infimum, but U is equal to infimum values. Okay, just we'll write this simple. Okay, but U is equal to, therefore U less than xn is less than xk is less than U plus epsilon for all n greater than equal to k, Okay, so therefore U minus epsilon less than U less than xk U plus epsilon for all n greater than k, right? So I can write U minus epsilon because U minus epsilon is a positive, and so U minus epsilon is less than U, so I can write this as U minus epsilon. I can write this chain. Okay, so now I will take only this. So what does this implies? U minus epsilon is less than xn U plus epsilon for all n greater than k, right? So therefore what does this imply? Mod of xn minus U is less than epsilon for all n greater than equal to k, and this is the definition. What? By definition, limit n tends to infinity, xn is equal to U, and this is nothing but the infimum of xn, n belongs to n. Okay, so the theorem is over now. Okay, so what we have seen here, a monotonic sequence which is bounded. If a monotonic sequence is bounded, then it is convergent. If it is increasing, then it converges to supremum. If it is decreasing, then it converges to infimum. So this we have seen. Okay, we'll see some examples of a sequence. Suppose we have the sequence xn, 1, 2, 3, 4, n . Okay, suppose this is the sequence termwise given. So this is what x is equal to xn is increasing sequence. Okay, this is the first example. Okay, the second, x is equal to 1, 1 half, 1 by 3, 1 by 4 . This is what then 1 by n . Each, so x is equal to xn is decreasing sequence. Yes, so this is what decreasing sequence. Okay, now third example we'll take. Third example is x is equal to 1, 2, 2, 3, 3, 3, 4, 4, suppose 4. What is this? may be repeated. So it's increasing, is increasing sequence. This is not a strictly increasing. This is the strictly increasing. This is the strictly decreasing sequence. Okay. So then fourth one, x is equal to so b square b cube dot b to the power n dot 0 less than b less than 1 is decreasing sequence. Now see, the powers are increasing here, but your value of b lies between 0 and 1. If you take any value lies between 0 and 1, now if you take the powers, so it will become smaller and smaller. If you take the powers of that, the number lies between 0 and 1, so then it becomes smaller and smaller. Okay, is decreasing sequence. So that means what? This is b square b cube. So this is what? This is a geometric sequence. This is a geometric progression, right? So this is geometric progression. So now, but b is what? 0. B lies between 0 and 1. So that means this is a decreasing sequence. So it will be a decreasing sequence. Now we'll take a problem. We'll take a problem on it. Let x1 is equal to, we have given the sequence like this. X1 is equal to 8, xn plus 1 is equal to 1/2, xn plus 2 for n belong to n. Show that sequence xn is bounded. Show that the sequence x is bounded and monotone find the limit. Solution. Let x is equal to xn be a sequence such that x1 is equal to 8, xn plus 1 is equal to 1/2, xn plus not xn plus 2, this is xn and 10 plus 2. Okay, so what we have to prove? It is monotone. First we have to prove it is bounded, and then it is monotone and something like this. Okay, so find the limit of the sequence. That means what? So if you prove it is bounded and monotone, we know that the monotone and bounded sequence is always convergent. So directly the question is what? Find the limit. Okay. So or they may ask like this: what? Show that the sequence is x is equal to xn such that x2 is equal to this is convergent. Okay. So for that we have to prove this is the monotonic increasing and bounded sequence. Okay. So note that the monotonic increasing sequence which is bounded above is always bounded. Okay. So this is what we have given. So we have to prove that it is the bounded. It is monotone. First we will prove it is monotone. Okay. So first we will prove it is the monotone sequence. So that means what? What we will do? Xn plus 1. Now see, we will write the terms first. Okay. So your x1 is what? 8. Your x2 is what? x2 will be what? x2 will be what? 1/2 x1 plus 2. Okay, so this is what? 1/2 into 8 plus 2, so that is 6. This is 6. Okay, now what is your x3 then? x3 is what? 1/2 x2 plus 2, so this is 1/2. x3 is what? 6 plus 2, so this is what? 3 plus 2, so this is 5. This is 5. Okay, so you will see that x1 is greater than x2, x2 is greater than x3. Okay, so that means what here? So xn is greater than xn plus 1. Xn is greater than xn plus 1. So what I will do now? I will make this as, I will multiply by half now. This is half xn is greater than half xn plus 1. Then I will add 2 on both sides. So the inequality remains as it is now. So 1/2 xn plus 1. So I assume that the result is true for n. Right? So what is this then? Now what is this then? Then this will what? Xn plus 1. This is what? Xn plus 1. Right? And this will what then? Xn plus 2. So that means what? Whenever this is true and this is true, x1 is greater than 2, that means the result is true for n is equal to 1, result is true for n, and then the result is true for n plus 1. Okay? So by mathematical induction, so x is equal to xn is, what is that? It is decreasing sequence. Is decreasing sequence. It is decreasing sequence. So that means we have proved that xn is monotone sequence. So therefore x is equal to xn is decreasing sequence. Therefore it is monotone. So we have proved first it is monotone. Okay, so therefore it is decreasing, therefore xn is less than x1 for all n. If it is decreasing, so x1 is what then? 8. This is 8 now. No need to prove this one, because what? It is decreasing sequence. Decrease the first term, right? The first term will be the upper bound of this one. Okay, so xn is less than n. So for all n belongs to n, we call this as 1. Right? So your xn is less than 8 now. So n will be the upper bound. So what we have to prove? It is a bounded. That means we have to prove it has a lower bound and it has the upper bound. So this is the decreasing sequence. Automatically the decreasing sequence is always bounded above. Your first term is nothing but the upper bound of the set. Okay. So this is the upper bound. So now we'll prove it is bounded below now. Okay. So since x1 is greater than 4. Okay. So now x1 is greater than 4. x2 is also greater than 4. x2 is also greater than 4. So what do I have to prove? This xn plus 1 is also greater than 4. You have to prove xn plus 1 is also greater than 4 now. Okay. So suppose xn is greater than 4. So your x1 is greater than 4. We'll suppose xn is greater than 4. If you prove xn plus 1 is also greater than 4, then we have proved. Okay. So what do we do now? Xn. So we'll multiply by half on both sides. So this will be 2 now. We are making this term now here. 1/2. So xn plus 1 means what? 1/2. So you have xn. So what do you want here? Xn plus 1. In the place of xn, you want xn plus 1. So we are doing this one. So what we do? We'll do this. This is your xn plus 1. So in total, we'll multiply by half. Then we'll add 2 on both sides. Then this is 1/2 xn plus 2 is greater than 4. Now this is 1/2 xn plus 2 is your xn plus 1. This is what? Xn plus 1 is greater than 4. Right? So therefore, by induction, by mathematical induction, xn is greater than 4 for all n belongs to n. Right? So therefore 4 is less than xn is less than 8 for all n belongs to n. We have already proved that xn is less than 8. Now we have proved that xn is greater than 4. That means your xn is less. Therefore x is equal to xn is bounded sequence. Bounded is bounded sequence, and it is monotone, and it is monotone. Therefore, x is equal to xn is convergent. Is convergent. Let limit n tends to infinity, xn is equal to L. Okay? So this is also true for limit n tends to infinity, xn plus 1. Okay? And this is equal to L now. This is equal to L. So L is already there. Okay? So therefore, limit n tends to infinity, xn is equal to limit n tends to infinity, xn plus 1. Right? So this is what limit n tends to infinity, xn is equal to limit n tends to infinity. What is your xn plus 1? Xn plus 1 is 1 half xn plus 2. 1 half xn plus 2. So this is what your L. This is 1 half L plus 2. 1 half plus. So what is this then? You will shift this to this side. This is 1 half L is equal to 2 now. 1 half L is equal to 2. So your L is what then? L is equal to 4. So therefore, limit n tends to infinity, xn is equal to 4. Is equal to 4. Okay. So now the problem is over now. So we'll take one more problem so that you will understand how to do this. Okay. So we'll take a second problem. Let x1 is equal to, so we'll take a small x1 actually. x1 is equal to 1. xn plus 1 is equal to root of 2 plus xn for n belongs to n. Show that xn converges xn convergence, and find the limit. It is convergent means if the limit is exists. Okay. Solution. If such sequences are there, always try to prove that sequence is monotonic, increasing or decreasing. So that we will do now. Solution. Let x is equal to xn be a sequence such that x1 is equal to 1, xn plus 1 is equal to 2 plus root xn, 2 plus xn only, 2 plus xn. So first we will check whether it is increasing or decreasing. Okay, so we find first few terms now. 1. So x2 we have to find. This is what? Root of 2 plus x1. So this is root 3. We'll find x3 also. So x3 means what? We have to put 2 now here. This is what? 2 plus x2 now. 2 plus x. So you have to put for x1, xn plus 1 is there. You want here x3. That means what? You have to put n is equal to 2 so that you will get x3 here. So this is 2 plus this. Your 2 x2 is what? Root 3. So this is what? 2 plus root 3. Now see here, 1 is less than x3. So your what? x1 is less than x2. x1 is less than x2. Okay. So let xn is less than xn plus 1. xn is less than xn plus 1. So if you prove that xn plus 1 is less than xn plus 2, then this sequence will be increasing sequence. Okay. So what you have here? You have to do this now here. xn. You have to do here xn plus 1. And you have to do what you want here? xn plus 2. Okay. So if you do this one, if you are able to do this one, then easily you will prove that the sequence will be increasing sequence. So that we will do now. So what you want here? You want here xn plus 1. That means what you want here? Root of 2 plus xn. So what? First we will add 2 on both sides. So first we will add 2 on both sides. So this is xn plus 1. Now we take the root on both sides. We will take a root on both sides. This is root on both sides. Okay. So now what is this? This is 2 plus xn. Is xn plus 1. And what is this? This is xn plus 1. That means this is xn plus 2. Xn plus 2. And this is true for all n now. This is true for all n. So therefore, by induction or by mathematical induction, it is better to write by mathematical induction. By mathematical induction, xn is less than xn plus 1 for all n. Just we will write this. Xn is less than xn plus 1. Therefore, x is equal to xn is increasing sequence. Is increasing sequence. Okay. So it is increasing sequence is always bounded below. Okay. So therefore, x1 is less than xn for all n belongs to n. So that is what? What is x1? x1 is 1. Is less than xn for all n belongs to n. I will call this as 1 now. So what I have proved? It is bounded below. Okay. So this is that is. Okay. So this is what that is. All this implies that. You can write this as what? Implies that. This is implies that. 1 is less than x1. That means all your terms are greater than 1. So that means 1 is the lower bound. 1 is the lower bound. We have to prove that now. We have to prove that the sequence is convergent. So what we have proved that the sequence is monotonic increasing. We have proved that the sequence is monotonic increasing. So if you prove the sequence monotonic increasing bounded above, if you prove increasing sequence is bounded above, so lower bound is always there. Lower bound x1 is the lower bound, right? So only I have to prove that it is the upper bound exists. So what we have to do? Only show that the upper bound is exists. So we will do for upper bound of the set now here. So so we want to find upper bound of this one. Now what is the x1? x1 is equal to 1. This is less than 2. This is less than 2. Okay. Suppose xn is less than 2. Suppose xn is less than 2. So if you prove this, xn plus 1 is also less than 2, then we are through now. Right? Then 2 will be the upper bound of the set then. Okay. So x1 is less than 2 now here, because what? 2 plus xn is there. So I have taken this and it is in the root. Right? So I have taken that as 2 now. So I want here xn plus 1. That means I want here what? Root of twice plus 2 plus xn now. So first I will add 2 now. 2 plus xn is less than 2 plus 2. So this is what? 2 plus xn is less than 4. I will take a positive root on both sides. So this will be what then? 2 plus xn is less than 2 now. And what is this? This is xn plus 1 is less than 2. So I have taken xn is less than 2 and I have proved that xn plus 1 is also less than 2. So therefore by principle of mathematical induction, xn is less than 2 for all n belongs to n. Okay. So I call this as 2 now. I will call this as 2. So from 1 and 2, 1 is less than xn is less than 2 for all n belongs to n. Right? Therefore, x is equal to xn is bounded sequence and monotone is monotone and it is monotone. Okay. So now monotonic bounded sequence is always convergent. Therefore, x is equal to xn is convergent sequence. Okay. So now we have to find the limit of this one. Okay. So let limit n tends to infinity, xn is equal to n. We want to find the value of this one. Okay. So therefore limit n tends to infinity, xn is same as limit n tends to infinity, xn plus 1 and this is L. Oh, this is small l. We have taken small l, we will write here small l now. Okay, anything you can take A, you can take B, whatever this you want. But for limit we have taken L now here. Okay, so you can take any number now here. So therefore, limit n tends to infinity, xn is equal to limit n tends to infinity root of 2 plus xn, 2 plus xn. Just I will write this. Now this is L now, and this is what 2 plus L now. Because limit xn, limit n tends to infinity is xn, 2 plus L. We will take the square now. L square is equal to 2 plus L. Okay? So it shift, one shift here now. So what is this? L square minus L minus 2 is equal to 0. Okay. So now the product is what? The product is minus 1. Product is minus 1 and sum is product is minus 2 and sum is minus 1. So these numbers are x L minus 2, L minus 2, L plus 1 now. L minus 2. The factor of this one will be what? L plus 1. Now see, the product is minus 2 and sum is minus 1. This is 0. So that means what here? N is equal to 2 and minus 1. Okay. But x is equal to xn is a sequence of positive terms. Is a positive terms. Therefore, L is equal to 2. L will not be minus 1. L will be 2. Now note that this is monotonic increasing sequence. Right? So what is your xn? Lies between 1 and 2. Xn is lies between 1 and 2. So your limit is also it should be 2 or this. Okay. So it is supremum will be the limit now. Okay. So n is 2. So therefore what? Limit n tends to infinity, xn is equal to 2. So that means what? This is the monotonic increasing sequence. It is bounded and it is convergent and it is converges to 2. Okay. So I have proved this one. Very simple example actually this is. Okay. So next we will do the second example. Xn is equal to, okay. So first we will write a question and then we will write the term. Establish the convergence. Establish the convergence or divergence of the sequence xn where xn is equal to 1 upon n plus 1 plus 1 upon n plus 2 plus plus 1 upon twice n for all n belongs to n. Okay, so we have given the term of the sequence. This is the nth term of the sequence is given. We have to discuss the convergence or divergence of this sequence. Okay, solution. Let x is equal to xn be a sequence such that, so your xn is what? It is given 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon twice n now. N plus n is twice n. So what we do? We will find xn plus 1. That means we have to add one more term now here. What? 1 upon n plus 1, 1 upon n plus 2 plus 1 upon twice n plus 1 upon. You have to add one more term. So this is what? Twice n plus 1. Twice n. So this is what? Twice n. You have to replace n plus. So twice n plus 3 will be there. Twice n plus 3. Your last term will be not this is twice n plus 2 last term. Here what? This is what? N plus 1. This is what? N plus n. Last term is what? Your n plus 1. Your one term is added now here. This will what? N plus 1 plus n plus 1 now. The last term is what here? N plus 1 plus n plus 1. Okay. So So here what, n plus 1 plus 1 and so on. Okay, so now, so this is start from actually n plus 2 now, not n plus 1 now. You are replacing n by n plus what? You are replacing by n by n plus 1. So this is what, n plus 2. It is started from n plus 2. So what we do? xn minus okay. So xn plus 1 minus xn will do. So what is this then? This is 1 upon 2 n plus 2 minus 1 upon all these terms are common to them. All these terms are common to both now. It will get cancelled. So only this term remains and this term remains. Okay. So now this is n plus 1. So we'll separate this n plus 1 minus twice n minus 2 upon so okay, we will simplify this actually. So this is what, 1 upon 2 into n plus 1 minus 1 upon n plus 1. So this is what, 2 into n plus 1. 2 into n plus 1. So what is this then? So here it is 1 minus 2 is there now. We have to multiply it. So this is what, minus 1 upon 2 into n plus 1. So this is what, this is less than 0. This is less than 0. This is what, less than 0. So therefore xn plus 1 is less than xn plus 1. Oh, we made a mistake here. Actually, here this is not the correct. So before this one, there is one more term. Before this one, there is one more term is there now. This is what? This is twice n plus 1 minus plus, no, this plus minus 1 upon n plus 1. No. So this is correct now, no problem for us. Okay, so this is twice n plus 1 should be there. Okay, so we'll write neatly now this. This is what you got, xn 1 upon n plus 1 plus 1 upon n plus 2 plus dot 1 upon, we'll write here n plus 1, n plus n. So before that, this is what, then n minus 1 plus 1 upon n plus n now. Okay, so here what, n minus. Okay, so we'll write here now xn plus 1. So this is what, then xn plus 1. So this is what you have to replace n. So this is what, n plus 2 then. Plus 1 upon n plus 3 will be there. Plus dot. Plus. This will be what then? 1 upon n plus 1. See, n plus 1 plus n plus 1 minus 1. So this is twice n plus 1. This is what? Twice n plus 1. Okay. So this is twice n minus 1. And this is twice n. Okay. Plus. Now you have to replace n plus 1. N plus 1. Plus n plus 1. Okay. What is that then? 1 upon n plus 2. 1 upon n plus 3. Plus dot. 1 upon twice n plus 1. Okay. So before that, here there is a twice n. Before that there is a twice n. Okay. See, this is 1. Okay. So before that, okay. So now so this is what? Twice n plus 2 now. Okay. Now before that, up to this terms are common now. This is what? Xn plus 1 minus xn now. So this 1 upon twice n plus 1 plus 1 upon twice n plus 2. These two terms are there. So these up to these terms are common to them. Up to this twice. This is what before that. This is 1 upon twice n. 1 upon twice n is there. Okay. 1 upon twice n minus 1. So this is what then minus 1 upon n plus 1 now. Okay. So what we'll do? This is what. First we'll do this one. So this is 1 upon twice n plus 1. 1 upon twice n plus 1. This is half now. Half minus 1. This is what then minus 1 upon n plus 1. Minus 1 upon n plus 1. We'll cross multiply this. We'll cross multiply this. This is what 2 is also there. 2 is there. This is 2 into n plus 1. So see here. 1 upon. I will take n plus 1. Now here 2 common now. First I will do this one. So see what happened this is. Minus 1 upon n plus 1. Minus 1 upon n plus 1. What will be this then? So this is what? This is 2 into n plus 1. You have to multiply and divide by 2 now. Okay. So this means then minus 1. Right? So this is what? Minus 1 upon twice n plus 1. Now we cross multiply this. This is twice n plus 1 minus twice n plus 1 upon. You have to cross multiply this. Twice n plus 1 into twice n plus 1. Okay. 2 into n plus 1 into twice n plus 1. So what is this? This will be this twice n get cancelled now here. So this is 2 minus 1. So this is 1. 2 minus 1 is 1 upon 2 into n plus 1 twice n plus 1. See whatever the value of n, this is positive now. So this is greater than 0. Whatever the value of this is positive. So what we get then? Xn plus 1 is greater than xn because this is positive. This is true for all n. This is true for all n, right? So therefore we may write this as xn is less than xn plus 1. See, xn is less than, right? For all n. So now your xn plus 1 is greater than xn. That means this sequence is increasing. So this implies that x is equal to xn is increasing. Is increasing sequence. Is increasing sequence. So if you prove this is what? Monotonic. We want to prove this is what? Monotonic increasing. This is increasing sequence. Only I have to prove that it is bounded above now. Only I have to prove it is bounded above. Right? So this is what? 1 upon n plus 1 is less than 1 upon n. Right? 1 upon n plus 2 is less than 1 upon n. And so on. So we can write this is what? 1 upon twice n is less than 1 upon n. Go on adding this. So what we get? Therefore 1 upon n plus 1, 1 upon n plus 2 plus that 1 upon twice n is less than. How many times you have to add this? N times you have to add this. So this is what? N into 1 upon n. Because everywhere this is 1 by n, 1 by n, 1 by n. You have to add this n times. These are the n terms. You have to add this n. So this sum will be what? The sum of a plus a is what? Twice a. A plus a plus a. So this is constant. You are adding 3 times. So this is 3a. If you a plus 4 times, then this is 4a. So same thing here what? 1 by n times. So n into this. So that means what is this? This is your xn. This is your xn. Is less than 1. Is less than 1. And this is true for all n. This is true for all n belongs to n. Right? So that means what you are. Therefore x is equal to xn is increasing and bounded above. Just we say above and bounded above. Because we have shown that there is upper bound, right? So therefore x is equal to xn is bounded sequence. Bounded and monotone sequence. Bounded and monotone sequence. Right? And we know that sequence is bounded and monotonic, right? Then it is convergent. And we have to discuss only the convergent or divergent. Therefore, x is equal to xn is convergent. Now the problem is over now here. Okay. So only I have to discuss the convergence and divergence of the sequence. So we have shown that it is increasing sequence we have shown that it is increasing and bounded above. So note that if a sequence is increasing, it is always bounded below. If a sequence is decreasing, then it is always bounded above. If sequence is decreasing, then it is always bounded above. So if the sequence is decreasing, you have to prove that it is bounded below. You have to show that there is a lower bound. Right? Sequence is decreasing. That means this is the first term. It is upper. But all the terms are greater than, all the terms are less than that number. Right? Sequence is decreasing means what? All the terms are greater than this number. That means this is what? This is bounded above now here. So only I have to show that it is bounded below. That means if a sequence is decreasing, show that it is bounded below. Right? So if a sequence is decreasing and bounded below, it is always bounded. Okay? So note that this. Okay? And if a sequence is decreasing and bounded below, then it is bounded, and then it is the convergence by monotone convergence theorem. Okay? So this is the monotone convergence theorem. I hope that you understand this one. Solve the number of problems on it. Okay? Okay, so we stop here. Thank you.